Hello everyone, I am Tejaswini Samanta. I am a high school student from India and I have been working on this project, probing a galaxy group with an FRB dispersion measure. So what are FRBs or fast radio bursts? FRBs are very fast and bright flashes of light that occur all over the night sky. They last for a very short duration of time, like just a millisecond. They occur outside the Milky Way galaxy, and since they are radio light and not visible light, we need radio telescopes to see them as they aren't visible through naked eyes. These FRBs occur very frequently all over the sky for like 4,000 events per day. Yeah. So now to understand how to probe a galaxy group, we need to know the matter distribution in the cosmic web. So what is the cosmic web? So the universe is very huge and largely constituted of dark matter. What we know about dark matter, it is invisible and forms a network of web-like structure, as you can see in this picture, and the gravitational force pulls them together. This large-scale web-like structure is the cosmic web. Now, apart from dark matter, the universe also consists of regular matter called baryons, that is actually plasma and neutral matter. These baryons are embedded in this cosmic web of dark matter and are extremely hard to detect as they are extremely diffused and ionized in this cosmic web. So, through this project, we will try to understand the baryons, that is, the plasma embedded in the cosmic web. For that, we measure FRB dispersion as it is known to be a very effective way of accurately estimating the amount of ionized matter, that is, the regular matter along the sightline through dispersion. So, what is dispersion? When light passes through a medium, let's suppose a prism in this case, it disperses or splits into 7 component colors. Why it disperses? Because the light with higher frequencies come faster as they have higher speed. So they differ in frequencies, which is why they differ in speed, causing a delay in time. Similarly, the FRB radio light behaves like a visible light and passes through the plasma medium in the space, and the light with higher frequencies arrive first on Earth. By measuring the delay between these frequencies, we would be able to tell the total number of free electrons or how much matter it has passed through. So the main focus of our project is FRB 2021-1203A coming behind from Centaurus A M83. The Centaurus A M83 is a group of galaxies in the constellations Hydra, Centaurus, and Virgo. This group can be divided into 2 subgroups called Centaurus A and M83 subgroups. Their mass is about 10-13.5 solar masses, and the distance from Earth respectively are 11.9 million light years from Centaurus A and 14.9 million light years from M83. The reason we are interested in the FRB 2021-1203A is because the radio waves coming from the FRBs directly intersects the group medium of the group of galaxies. What we wish to study is the contribution from the group to the FRB dispersion measure. However, first we need to account for the other background galaxies. In this project, we will estimate the dispersion measure contribution of foreground galaxies that are not in the Centaurus A M83 group but still foreground to the FRB. We will measure the distances to the galaxies using the Hubble law, which states that objects that are further away from Earth appear to travel faster because of the expansion of the universe. By measuring the speed of the galaxies, we can measure how far they are, and we estimate the speed through the Doppler effect. I assume everyone has heard the sound of an ambulance that it makes while moving. So when it moves towards us, we hear a shrill sound, and when it moves away from us, um, the sound like it gets lowers in pitch than it was when we hear when it's coming towards us. We call this effect the Doppler effect, which essentially happens when the source of the wave is moving towards us, and it causes the frequency of the wave higher than what it's normal, and vice versa when it's moving away from us. When light rays are subjected to the Doppler effect, we can use Doppler effect for light to measure how fast galaxies are moving. Due to the Hubble law, the galaxies that are further away from us appear to be traveling away faster. Light from galaxies appear to have a lower frequency than expected because of their redshift. The light coming from the galaxies have a slightly redder tinge and slightly redder wavelengths than normal. It is just like the ambulance example we have used in the previous slide. And hence, the more distant galaxy is, the faster it's moving, and hence higher its redshift. And this is how we estimate how far away galaxies are from us. So now that we know the background of the project, we will talk about what data is processed. We processed multi-object spectroscopic data from the Gemini Observatory situated in Chile. We used a Python package to process the data. The image we are seeing on this slide is the raw image, which is unprocessed from the GEMOS observatory. Just as when light passes through the prism, we see rainbows. And what we see here is the light from a galaxy passing through a dispersion measure that is set on top of the instrument. And what the image we see is basically all those rainbow of a lot of galaxies. So this image we can see is like these vertical lines. All of them basically correspond to an object or a galaxy. So since this is raw and we need to define this to understand what data we can obtain from this. Now I highlight the reduction procedure that allows us to extract useful information from the raw images. Basically convert the 2D images to a 1D spectrum. So as you can see on the left, we have a section of that image that was shown to you before. Um, and we can see that many of those vertical lines have been labeled with their objects, which all of them correspond to the to a different galaxy. And on the right, we can see a graph or plot that that corresponds to a single object on the left side image. And as we can see, the image on right is much easier to understand and useful to us to extract those information. So while doing this, we faced a lot of challenges. The major one was that Bible struggles with wavelength calibration, specifically for the Gemini Observatory spectra. The wavelength solution is distorted, which basically means that what happens is when Pipel tries to do that, it has an archive of different wavelengths that are present in the universe, such as argon or hydrogen emissions. And when we feed it a particular image, it tries to compare with its archive and assign each emission line that it sees with value of a particular wavelength. So sometimes Python does its job pretty well, and sometimes it can't really assign those values very well, leading to inaccuracies. So we need to sometimes manually calibrate the same wavelength values for many slits to get a better reduction overall. So how we do that? We can see a lot of emission lines on this graph. we have to manually try to assign them as to what it should be. Now, doing this by hand is a very time-consuming and lengthy process. So this project is still a work in progress. Now, we got some results, and we reduced spectra from 34 objects in our data. Out of those 34 objects, 8 redshifts were assigned with high confidence. Now, why were we able to assign only 8 redshifts? Because in our original data, there were many low light emissions, and they were not really easy to be assigned. So out of those 8 objects, 4 were found to be in the foreground. That means their redshift were less than the redshift of the galaxy, that the group of galaxy that the FRB was observed in. So with that, there is a lot more work that needs to be done. We need to reduce data from the A omega spectrograph to obtain 400 more redshifts of closer galaxies. We need to obtain galaxy distances from existing catalogs for the local volume galaxies, including the Centaurus A M83 Group. And we need to obtain galaxy stellar masses through SED fitting, and finally obtain dispersion measure contributions from the foreground group of galaxies. So with that, I would like to thank all of you for your time.